Swayam Prabha. Digital India. Educated India.
Okay, so welcome back everyone, and in this module we are talking about symmetry and conservation principle. So symmetry and conservation principle. Okay, so we talk about the existence of conserved quantities and how it is related to the symmetry of the Lagrangian, right? So the main focus here is the existence of the conserved quantity which is going to how it is linked with the symmetry of the system. So we are going to introduce two results for specific cases and then we'll generalize the result. So the first result that I have is the invariance of V under translation. The invariance of V under translation. So let us say that let S be a conservative principle, be a conservative standard system. So we are talking about the specific case. So conservative standard system with potential given by V, with potential V. Okay, so now if S is translated, if S can be translated parallel to a constant vector, right? So if it is translated parallel to a constant vector n without violating any constraints, and if V is unchanged by this translation, what we see is that the component of linear momentum in the n direction is conserved. So the nth direction linear momentum is conserved. The nth linear momentum is conserved, and in this case let us quickly see the proof of this result. So let us denote Ri be the position of S, right? So Ri be the position of S with let's say vector Q as a generalized momenta, as the corresponding point in configuration space, corresponding point in the configuration space, and let us say the displacement lambda in the nth direction is given by let us say r lambda. So from r we will go to r lambda. So that is my corresponding transformation, right? So now, which means that this transformation is very simple. Since we are only talking about translation, which means that Ri lambda will be equal to Ri plus lambda times n. So Ri lambda is Ri plus lambda times n, and this is going to be corresponding to q lambda in the configuration space, qi lambda, right? Okay, so then what we have is, so what do we get? So Ri is equal to Ri lambda. Now, so the initial condition we can quickly state for lambda equal to 0. We see that Ri lambda is Ri, and or what we have is Q lambda is Q, right? And then we can quickly write down the jth Lagrange equation and try to simplify the jth Lagrange equation in the following way. So what we get is, let us say we multiply the jth Lagrange equation by partial Qj partial lambda, and at lambda equal to 0, and we see that this is going to be summation mivi dot with partial Ri partial Qj, right? And we see that this is also equal to, on the right hand side for the conservative system, this is going to be partial V partial Qj times partial Qj partial lambda, right? And we can now rewrite this entire stuff. We sum over for all j, and we find that this is summation I times mivi dot times j from 1 to n partial Ri partial Qj and partial Qj lambda partial Q lambda, right? So that is what we have, and this is at lambda equal to 0. Okay, so then what do we get? So this is on the right hand side, this is going to be summation over j 1 to n partial V partial Qj times partial Qj partial lambda, and we can quickly see that this right hand side, we can quickly simplify everything. We see that this quantity on the right hand side is going to be this quantity inside this curly bracket, this one. So this one is nothing but summation j from 1 to n partial Qj lambda times Ri of Q bar partial Qj lambda by partial Q lambda. So this is at lambda equal to 0, and this is going to be nothing but we can quickly simplify that this is equal to d lambda of Ri of Q lambda, right? And this is at lambda equal to 0, we find that this is going to be d lambda, and if we plug in the expression for dri lambda, we get that this is equal to n. Okay, so then what we have is we see that similarly the right hand side is nothing but d lambda of vq lambda, right? So this is the partial derivative of this, and we see that this is also equal to 0. So we have that we got the potential now is unchanged, right? So finally what we get is, after utilizing all these simplifications, the expression that we get is summation mivi dot with n. So that is the n that we have. This is on the right hand side is equal to 0. So what we get is that the momentum, the component of the linear momentum along the direction n is conserved. So this is our linear momentum mi. So mivi dot is 0, or from here we get that summation mivi dot n is going to be a constant, which is the component of linear momentum in the nth direction. So linear momentum. Okay. So then we can have a similar theorem in the form of the rotation operation. So let me write down the statement of the problem. So the problem says So invariance under rotation. We see that let S be a conservative system. Let S be a conservative standard system with potential energy given by V, right? And if S is rotated about a fixed axis, let's say about a fixed axis, O comma K. So we have to fix the axis. We have to also fix the point, the origin point, again without violating constraints. Without violating constraints, we see that and V of Q, the potential is unchanged by rotation, right? We see that the angular momentum of S about this O comma K axis is conserved, right? And the proof of this result is almost identical to what we saw in the previous theorem, where now we are going to rather use the fact that dri d lambda is K cross with ri lambda, which means now since we are experiencing rotation rather than translation, we expect that this derivative is going to be K cross ri lambda, right? So this is the rate of change of rotation with respect to lambda. Okay, so I am not going to continue with the proof of this because the proof is almost identical, and we will directly state the result that what we see is that summation mi vi dot times K cross with ri comes out to be summation mi ri cross with vi, and what we see is so mi ri cross with, what we have done is we have from here we have integrated the expression, so we have integrated the expression, and we see that this mi ri cross vi will be a constant, and that is where we see that the angular momentum is again conserved along the axis of rotation, along O comma K. Okay, so now let us generalize. So these were two operations, one was translation, the other was rotation. How about we provide a general operation, like where the rotation and the translations are specific cases? How about we provide a general operation in the form of a mapping operation? So let us denote the general operation in the form of, I'm now going to state the result, which is the basis of the result of the symmetry of Lagrangian, in the form of the so-called Noether's theorem. So the theorem says, again, let S, we simplify, let S be a holonomic system, holonomic system with Lagrangian given by L of Q comma Q dot comma T, right? And let M lambda be a one parameter family of maps, and such that we map our Q with M lambda to Q lambda, and we see that in this case we have that, again, the map is such that q lambda is equal to q itself, the generalized coordinates are mapped back to its original value when lambda is 0. At lambda is 0, and we see that if we have that m lambda leaves, so in this case it leaves our Lagrangian as invariant. It leaves our Lagrangian invariant, right? So so which means that what we are saying is L of q lambda comma q dot lambda comma t is the same as L of q comma q dot comma t, right? And then let us see the proof of this result. So what we have, so let us say q of t, so let q of t be the configuration. Let q of t be the configuration of S, which is, let's say, which is a solution to this system, which is a Lagrange equation. So which is a solution of our Lagrange equation. So ddt of partial L partial qj dot minus partial L partial qj, and this is equal to 0. And now let us let us write the Lagrangian in terms of the generalized momenta. So we see that this equation can be, the Lagrangian equation can be, the Lagrange equation can be rewritten as follows. We see that this is Pj times partial Qj lambda partial lambda at lambda equal to 0, and this is also equal to ddt of partial L partial Qj dot of partial Qj lambda partial lambda. This is at lambda equal to 0. Okay, so what we get is, now if we were to rewrite this right hand side using chain rule, this is what we get. So this is going to be ddt of partial L partial Qj dot times partial Qj lambda partial lambda at lambda equal to 0, and plus partial L partial Qj dot times partial t of partial Qj lambda partial lambda. Okay, so what we have is, now what do we get? So this is at all at lambda equal to 0, by the way. So now we see that I think that this expression is fairly clear from the chain rule expression, because what we see is, let me expand this, why we get this expression, because the ddt of partial qi lambda partial lambda, this is equal to summation k from 1 to n partial q k partial qj lambda partial lambda times q k dot, and we see that this is partial lambda times summation partial q j lambda by partial qk times qk dot, right? And we see that this can be rewritten as partial qj dot lambda partial lambda, right? So this is via the chain rule. Okay, so then let us call this last expression as star. Okay, so let me use this expression star now. So from star I can simplify this expression as follows. So my partial L partial qj times partial qj lambda partial lambda, right? This is at lambda equal to 0, and the next expression is partial L partial Qj dot this is partial L, so partial Qj lambda partial lambda, right? So this is at lambda equal to 0. So this is going to be partial Qi lambda of L of so now we are now clubbing everything together. So this is going to be the Lagrangian at q lambda comma q dot lambda comma t times partial q lambda q del lambda plus what did we get? So then plus this is going to be partial q j dot L q lambda comma q dot lambda comma t and then partial q dot lambda comma partial lambda. So this is the second expression which is expanded. So this is at lambda equal to 0. So then let me now look at let us now sum this expression, this new expression double star. So what is that we get? So summing double star, we get that for all j, we see that the time derivative of this generalized momenta summation pj partial qj lambda partial lambda, this is at lambda equal to 0. This is going to be this is going to be the same expression here, summation j from 1 to n partial qj lambda partial L lambda partial qj lambda partial lambda plus partial L lambda partial q dot qj lambda times partial qj lambda by partial lambda. So we see that this is the expression, again this is at lambda equal to 0, and since we expect that the Lagrangian is invariant with respect to the map m lambda, we see that partial why this right hand side is 0, because we see that this is nothing but we have used the fact that partial dd lambda of L of q lambda comma q dot lambda comma t is the same as the one without the derivative without the map, which is d L of q comma q dot comma t. So or the Lagrangian is invariant under the map m lambda. So we have that this is 0. So hence that is why the right hand side is 0. I think we are almost done here. We see that this expression on the right hand side of double star is 0, but on the left hand side this was nothing but related to the generalized momenta. So from this expression we can derive that ddt of summation j from 1 to n of pj partial qj lambda partial lambda, this is at lambda equal to 0, this is the value which is given by 0 because of the right hand side. And I think we are all done here. We can quickly say that this summation inside this derivative summation j from 1 to n pj partial qj lambda by partial lambda is at lambda equal to 0 is a constant of the system, and that is our the linear momentum along the generalized coordinates qj. So if the Lagrangian is invariant under the map, then the corresponding momenta, the generalized momenta, is conserved, and that is the result which we call as the Noether's theorem. And we can see that the result is quite general as long as the system is holonomic. And the moral of the story here with this result is that if you have an invariance of the Lagrangian along a certain coordinate, along a certain generalized coordinate, then the generalized momenta along that coordinate is conserved. Okay, so let me rewrite the result. So this is how we will use the Noether's theorem in subsequent discussion. So an invariance of the Lagrangian is the constant of motion. An invariance of the Lagrangian is the constant of the motion, and that is a conserved quantity. Okay, so let us wrap up this discussion here, and in the next discussion I will be talking about the idea of Hamiltonian. We will also introduce Hamilton's principle, but in the meantime, in between, I will also introduce the case of Legendre transformation, and how through Legendre transformation we can relate the Hamiltonian with the Lagrangian. Right? It is the Hamiltonian which is more known by the community, the physics community, than the Lagrangian. The Lagrangian is more of a mathematical construct. So thank you so far for listening. Thank you very much.